Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to be talking about standing waves, guitar strings, and electrons. So in this video we need to talk about the electron and how it behaves in the atom, and we're going to have to first talk about standing waves and guitar strings as an analogy to help us understand how the electron is behaving in the atom. So just as we discussed in a previous video about the nature of light or electromagnetic radiation can be seen as either a particle or as a wave. It displays both properties, and we know today that the electron also displays both properties too. So the electron can be seen as behaving like a particle, or it can be seen behaving like a wave. And so the modern model of the atomic structure or of the atom is a little bit more complicated. So we have to kind of take in consideration the wave-like behavior of the electron. So before we can get into the wave-like or waveforms of the electron, we need to look at the waveforms of standing waves. And we're going to use a guitar string as an analogy. So let's get into this. So when you're playing the guitar, when you pluck the strings of the guitar, you are putting a certain amount of energy into the string. The harder you pluck it, the more energy that goes into the guitar string, and then it creates what is called a standing wave. Well, what is a standing wave? A standing wave is where the ends of the string are fixed. So I have, for example, this is one end of your guitar string that's fixed on this end and one on this end. And so when you pluck the string, the wave doesn't propagate this way, it stays in place. But when you look at it, it will look like it's propagating, right? And so the way this works is when you pluck the string, you can see at various times, stand on this side so you can see better. So at various times, this is the way the string looks. So as it's vibrating, the parts of the waves are going up and down. The wave is going up and down at various parts of the wave, various spots. So if we pick this spot, you can see that, okay, this is the highest or largest part of the wave, and then it's going to come down. So it's starting to come down until it flattens out, and then it starts to keep coming down. And so this part of the wave is going down, while this part of the wave here is going up. So it's fluctuating as well. So this part of the wave is moving up, right? And then it flattens out, and then it's still moving up until it reaches a maximum. And then what's going to happen is that this part is going to go down again, right? So flattens out, goes down, and then it's going to go back up. And so it's vibrating and it's moving up and down. So every part of the wave is moving up and down at various parts, except for a few, and I'll talk about those points in a moment. So basically what happens is when you pluck the string, you're causing it to vibrate, and so the wave is going up and down, as the string vibrates. Okay, so if we were to superimpose all of these snapshots into one, right? So here we have the snapshot. This is what you would actually see when you pluck the guitar string. So if you've ever seen a string that's moving really fast, you might have seen, and you're looking at the wave like this. If it's a standing wave, it'll look something like this with the string vibrating here. It looks blurry here, and then you got this here, and so you've got this going on when you're looking at it. So this is what it looks like when the guitar string is plucked and the string is vibrating up and down really fast. You see something like this when you're looking at the string. Now you'll notice that there are actually parts of the string or points at which the string actually does not move at all. So here and here and here. Obviously, if the string is attached to a fixed like wall or structure or something like a guitar string, then this end the ends of the string are not moving; they're stuck in place. But you'll notice that everywhere on the string you have motion except for these particular points here, and these are called the nodes. There's absolutely no motion at those points on the string. They stay in place, right? So this is what your guitar string looks like. Now, as I said, depending on how hard you pluck it, you get different waveforms, right? So if I pluck it a little bit, if I give it a little bit of energy, then it looks like this. I have a half wave here, right? So one half wave is here if I pluck it with a certain amount of energy. If I pluck it with another amount of energy, a higher energy, like if I pluck it harder, I can get two half waves. So I can get a full wavelength here or two half wavelengths. Right here, I only have a half wavelength, right? So just to remind you, a full wavelength is when you go from one point to an identical point on the wave. So here it's going up, comes down. That's not an identical point because it's going, I'm moving down. Now I come back up here. So I was coming up here and now I'm going up here. So these two would be identical points, right? So same thing here. If this is my wave, right? Right? So if I look here, this is my wave. So it's going up, coming down, going up. So this and this. From here to here would be a wavelength, or from here to here would be a wavelength. So this is the exact same spot as this one. They're identical points. So it could be the same here, like from here to here, from trough to trough would be a wavelength. So, but a half a wavelength would be here. So from this would be a half wavelength, this would be a half. This would be a whole, right? So same thing here. If I pluck my guitar string with a certain amount of energy, I get a half of wavelength. And so I get this waveform here. If I plug it with a little bit more energy, then I can get two half wavelengths or a full wavelength, right? If I pluck it even harder, I can get three half wavelengths. So there's only there's a lot of different waveforms that you can get, like almost maybe infinite theoretically, right? But those waveforms are limited, right? I can't get a one way. I can't get a half and a quarter. I can't get three quarters of a wavelength because the form is limited by the fact that I have the string tied down at both ends. So it will only allow for certain waveforms that have a certain amount of energy, right? So if I pluck the string with a certain amount of energy, I can get a half a wave, right? If I pluck it with another amount of energy, I can get two half waves. I am not able to get anywhere in between that. I can't get between, oops. Sorry about that. So I can't get something that's between a half and two halves. I can't get three quarters of wavelengths, right? Because it doesn't allow for that. So I can only get a half or two halves or three halves or any whole number of halves. Here I have four halves or two wavelengths. I could pluck it even harder and add a fifth half, so I could get it maybe to get five halves or six halves or so on. I can only increase my increments by a half a wavelength. So that limits the number of or the kinds of wavelengths I can get or the kind of waveforms I can get in my guitar string. So that is an introduction to standing waves and guitar strings and different waveforms that you can get in your guitar string. So what does all this have to do with the electron? Well, the electron as I said earlier, has particle-like characteristics, but it also has wave-like characteristics. It can behave like a wave. And so the modern model of the atom, it treats or understands the electron's motion as a wave in the atom. And so that's so understanding the electron as a standing wave in the atom helps us understand the different energy levels or the orbitals that we're going to talk about. So let's get into that. Okay, so let's apply what we've learned about the standing wave and guitar strings to the electron in the atom. So when we're looking at the electron in the atom, we view the electron as behaving in like a standing wave. So there are some descriptions of this character that apply that are the core of modern atomic theory. So let's go over these particular descriptions. So the following statements here are the core of the modern description of the wave character of the electron in the atom. So, number one, just as the intensity of the movement of a guitar string can vary, so can the intensity of the negative charge of the electron vary at different positions outside the nucleus. So we saw in the guitar string that the movement, the string can vary in its intensity, right? So as the string goes up and down, that up and down motion can be less or more or less intense. And so the electron charge can be more or less intense given its position outside the nucleus. So as the electron gets further away from the nucleus, its its electric charge, its negative charge is less intense, but as it gets closer to the nucleus, it's more intense. Okay. So number two, the variation of intensity of the electron charge can be described in terms of a 3D standing wave, like the standing wave of a guitar string. So the guitar string, because it's a guitar string, is tied into two places, and so its standing wave is two-dimensional. But we can think of the electron since, oops. Sorry about that. So, since the electron is traveling around the nucleus in a three-dimensional space, and we want to think of the electron's nature as a wave, so it makes sense that we would think of the wave nature of the electron as described by a three-dimensional standing wave rather than a two-dimensional standing wave. Three, as in the case of the guitar string, only certain waveforms are possible in the electron in an atom. So what that means is that just as we saw in the guitar string that if you put in certain amount of energies into the guitar string, you can have it form different waveforms, right? So you can get a half wave, you can get a full wave, you can get 1.5 waves. So you can increase incrementally by half waves. And so you're limited by the increments of half waves, and therefore the amount of energy you could put into the guitar string to get those waveforms is limited as well. So the same thing goes for the electron. The electron in the atom, since we're treating it as a standing wave, therefore the electron can only have certain energies that are tied to the allowed waveforms of the electron. And so these waveforms, these allowed waveforms, we're going to refer to as orbitals, and we'll talk about that in a little bit. So again, the electron's energy and waveforms are limited in the atom. So there's only certain waveforms that the electron is allowed to have. And then finally, we can focus our attention on the waveform of varying charge intensity of the electron without having to think about the actual physical nature of the electron itself. So that's like if we ignore the guitar string and just focus on the blurry part of the waveform of that guitar string, we can ignore the fact, well, the guitar string's made out of a certain material and so on and so forth. We can ignore all that and we can just focus on the waveform of this string itself, the blurry part, and say, oh, this waveform of the guitar string has one half wave, or it has two half waves, or it has two full waves, and so on. So we can focus on that rather than on the guitar string. So in the same way, we can focus on the waveform of the electron without having to think about where the electron actually is, or what the electron's nature actually is, or the physical nature of the electron, or anything like that. We can just focus on the waveform itself. Okay, so let's now go into orbitals and apply this to orbitals and make a little bit more sense of this, hopefully, when we talk about the orbitals. Okay, so let's talk about orbitals now. So let's remind ourselves about our standing wave. So here we have a standing wave. And as I said, the lowest waveform that you can have on say a guitar string or a physical standing wave is this form here, where you get one half wave spanning the whole from one end of the string to the other. So this is the simplest, lowest energy waveform you can get for your guitar string. Now, so you can have an analogous thing happens with the atom, the electron in the atom. So again, if we're looking at the electron as behaving like a three-dimensional wave, then the lowest energy waveform that electron could have would be, something akin to this. And so if you look here, this would be the 1s orbital, and this is the way the three-dimensional waveform looks for the electron in the atom. So this is the lowest energy orbital for an electron, and you can see that it has a spherical shape to this. So the wave view views this as a cloud, and so pardon my drawing here. I did the best as I could. So this is supposed to be a cloud where you can see that it's darker towards the center and it gets lighter as you go out, meaning that the intensity, the charge intensity of the electron as you get closer to the nucleus is greater than when you get out farther from the nucleus. So you can see that the intensity is less out here, so the charge intensity gets lower. And so we can define an orbital according to the wave view as a cloud. And so if we look here, we can define the orbital as the volume that contains a given high percentage of the electron charge. So typically it's 90% or 99% or whatever percentage you're looking at. Typically 90% is what we're looking at. So this might be the volume that contains 90% of the charge intensity of the electron in this orbital. And so we call this the 1s orbital. It has a spherical shape to it, three-dimensional. And so again, this is akin or analogous. The guitar string is analogous to the orbital. So this would be the three-dimensional waveform of the electron in the atom at the lowest energy level. We call this the 1s orbital, right? Another way that you could look at this is from the particle point of view. So if we were to take a snapshot of where the electron would be at any given moment, that would create a dot. The dot would represent that the electron is there at that moment. If we just kept taking snapshots and finding where the electron would be at, the particle view of the orbital kind of creates a map similar to this, but here we're looking not really at the percentage of of electron charge, of charge intensity, we're looking more at the probability of where you're likely to find the electron. So another definition according to the particle view would be that the orbital is the volume within which an electron has a high probability of being found. So again, that percentage, typically 90%. So here we have what is called a probability map, right? And you can see again, towards the center, you can see that it's darker. You have more dots here clustered here. The density of the dots is larger here, but as you get farther out, the density or the clustering is less. So it's less clustered out here than towards the center. So what that's telling us is that the probability of finding the electron is greater towards the nucleus, and the probability of finding the electron is less as you get farther away from the nucleus. And so this probability map represents the 1s orbital. And again, the orbital in this context would be the space or the volume in which you have a likelihood, a 90% probability of finding the electron somewhere in here. A higher probability towards the center, a lower probability towards the center, but a 90% overall of finding the electron somewhere within this spherical volume. And so that is how we understand the orbital. And so again, orbitals are just waveforms of the electron. So different waveforms are represented by different orbitals. So in this case here, I wanted to kind of show here that just as you put more energy into the guitar string, you can get a wave like this rather than a half wave here. Here you have a half wave. More energy I could put in 2 half waves, right? So now I have 2 half waves, and this is going up and down. So now in the same way, you can see that you have an orbital in the same way with here. So this would be our this would be the 2s. That would be the 2s orbital. And so notice here we have a node. This is where the string is not moving at all. And so you would have a node in the 2s as well, where you kind of have a sphere within a sphere, right? So you have a larger sphere within another sphere. And so here you have like a shell where there is no probability. I did my best to kind of make that visible, but hopefully you can see that there's a space here where there's no dots. And so that would represent the node. There's no probability of finding the electron this particular distance away from the nucleus. And so you get a node in the orbital here, your 2s orbital, right? So the 2s orbital has a node in it, and it's larger. Well, I didn't really draw it larger, but it should be larger than the 1s, right? So this should be larger than 1s. I didn't have space for that, but just FYI. And so the 2s orbital has this node where there's 0 probability of finding the electron. So at that distance, so it's like a shell of no probability. But outside that shell, you have some probability. Inside that shell, you have a larger probability. And so these are orbitals. And so again, the orbitals are like the guitar strings. They're the waveforms of the electron in which you're going to find a high intensity electron intensity or charge intensity or a probability of finding the electron. And so that's what we mean by orbitals. I hope this was clear. This is a pretty tough topic to try to explain, but I hope I did my best. And if I did, if this was helpful to you in any way, then please like the video, share the video with your friends. Make sure that you hit the like button over there. Also, subscribe to my channel, hit that notification bell when you do, and click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. If there's a video you want me to do for you on a particular topic, just let me know, and I would love to do that for you. Thanks for joining me, and have a great day.